In our first talk, led by Jan van der Assen, we will hear about a container-based system for malware analysis. Jan is a researcher at the University of Zurich, focusing on risk management and the mitigation of cyber threats. Jan, the stage is yours.
Okay. Yes, good morning, everyone. It is a pleasure to basically start this second day of SDS 24. And as just announced, this talk is within the realm of cybersecurity, more specifically about our work on SecBox, which is a lightweight platform for dynamic and reproducible malware analysis. So first, the broader motivation. Malware still a relevant. Okay, I'm not sure. I think we're moving backwards now.
The virus.
Yes, that's it. That must be it.
The green one is full.
Yes. Okay. So if we look at just some statistics from one ETH report I picked, this was basically on supply chain attacks in cybersecurity. We saw some of the malware attacks persisting for even more than 1 year. But nowadays, don't we have all of this fancy and accurate AI-based detection? So in the past, we have looked quite strongly into static features, so bits and bytes, numbers, numbers of lines of code. But nowadays, we can see a lot of research gravitating more to behavioral-based fingerprinting and more accurate detection. So when we look at a, let's say, very standard machine learning pipeline, and also consider that malware is quite a morphing threat vector, so for example, ransomware is still quite relevant today, but this is something that we have been discussing for almost 30 years now. And we want to achieve detection based on behavioral data, then what we need is basically dynamic execution here. So something that makes this quite a bit more challenging is the frequency at which we collect those samples. So I picked one random malware sharing database from Switzerland, and we see roughly 300 samples being collected within 24 hours. And when we basically map this motivation to what we find in both the literature and in practice, we can find a number of limitations in collecting this data. So the first one is, how can we securely execute those samples and collect data, especially if we look at Linux-based samples? Then how can we explore more lightweight isolation mechanisms? So a lot of this work is still focused on virtual machine-based isolation. And depending on your company, it may not be very feasible to spin up 300 virtual machines every day and use this for your analysis. The third factor is basically reproducibility. So maybe you gather some data with a specific interaction with the malware or the malware with its environment, and at some point you have to recreate this data set. And the third, the last, something about this clicker is going very strange. Okay, I'll try again. So, and the last part is basically real-time visual exploration of heterogeneous data. So the contributions of this work are basically the platform I mentioned earlier. So it is SecBox. It's a container-based malware analysis platform. So the first contribution is basically the modularity of the platform, which enables secure execution decoupled from the data collection and from the infrastructure. Then we are exploring the usability of using containers for executing malware, and the integration of Linux-based artifacts and images. We want to enable interactive yet reproducible analysis, and also considering a post-mortem stage for various dimensions. So all of these features we have subjected to various experiments using real malware. So we looked at performance, isolation, and visibility, monitorability, so which kind of data we can extract, and the automation of the overall process and the reproducibility. So let's go through the architecture. So at the core, we have basically sandboxes. So you can see there are always two of them, an infected one and a healthy one. So we always deploy 2 containers, which are basically just Docker containers, but with a hardened hypervisor. And both of them use the same base image, and only one of them, of course, will see the malware artifact pre-deployed. And the main idea here is that we could execute the same benign behavior in both of them, but one of them being subject to the execution of the malware. Then we also see a controller, which basically manages the life cycle of the sandboxes. It relays the user input and output in terms of shell commands. And then we have monitors. So these are basically the ones gathering data. So these are basically 3 dimensions in particular. So system calls, capturing the interaction from the malware with the kernel, basically, network traffic, and also performance. So basically which resources are consumed. Then within the data layer, we have data managers. So those basically receive the data collected by the monitors, and they process and persist them. They will also do the data mining post-mortem. So for some of the more volumetric aspects, such as system calls, those are not persisted in, are not collected in real time. But for some of them, we see real-time processing, so that during the interactive analysis, you already get some insights. And then we have a simple web API. So the web app has 2 functionalities. So the first one is to collect data or malware samples from some malware exchange databases. And of course, also the interaction with the front end, which is then basically the last component needed here. So in the front end, you basically first walk through it as follows. So first you select a base image. So for example, you want to say I'm using this particular version of Linux, and I'm looking at some specific malware artifact, let's say a Monty ransomware. Then you perform interactive analysis first. So there you have basically 2 user shells, so you can interact with both the infected and the healthy instance. And of course, only in one of them you can interact with the malware. And then once you conclude this interactive phase, you would do post-mortem analysis. So there you see the mining of and annotation of system calls, network, and resource metrics. Then we also see in the front end reproduction as a kind of cross-cutting concern. So how we achieve reproducibility here is through what we call playbooks. So these record the user input and the timing, the relative timing when it is done, so that later on you could essentially replay the exact interaction with the malware. Yes, so it would look something like this. So here we see first the interactive stage. You can see on the left and on the right, you can see some first performance metrics giving you an indicator of how the 2 sandboxes behave in terms of these resource metrics. And in the center, we can see the 2 shells. You can also see here basically the command line that you have here. You can see it is not split. So if we enter a command here, it will basically be executed both in the infected and in the healthy instance. And you could also basically split. So you could only interact with the infected one if you want to interact only with the malware sample. Once you conclude this interactive phase, here we can see the post-mortem analysis. Here we can see that we can add new, let's say, analysis requests. So for example, here we see the network traffic being processed and analyzed by means of the distribution of network layers in that sense. Then looking at some of the evaluations that we have done using this platform. So the main goal is to basically show the functional and qualitative features of the platform. And we want to focus on the following properties. The first one is the isolation provided of the sandboxing component. So of course, here it is quite relevant that we can ensure that the malware doesn't leak to the underlying infrastructure, because after all, this is basically malicious software we are executing here. And quite related to that is that we want to achieve basically low visibility against some of those samples, right? So we could perhaps use something very strong, so isolating completely from the infrastructure. But then the challenge is that this may be perceived by the malware. So there are some malware samples that try to really detect are we in an isolated scenario? And if so, they will obfuscate their behavior. Then, yeah, the title already mentions it. We try to enable a lightweight platform. So, of course, the performance requirements of the platform are key. And then the automation of the process. We want to see how much of the platform can be automated in terms of the overall process. And here, quite related, is the reproducibility of this. So can we achieve consistent results if we want to recreate data sets with the user interaction considered too? And monitorability also popping up here. Yes, so basically just what kind of data can we extract here. So first looking at automation and reproducibility. So what do we mean by reproducibility? So we are talking about the ability of the platform to achieve consistent outcomes. First, why do we even need reproducibility? Why is it important in this scenario of extracting data from malware? So something we would like to do perhaps is to update some of our detection models that we have nowadays based on a newly collected sample. So this could work something as follows. So perhaps some kind of incident response team, someone actually working operatively in the cybersecurity field could perhaps flag. This is really going crazy. I have no idea if I'm doing something wrong or not.
Just push hard when you want to.
I'm not clicking anything and it's moving forward. But yeah, we can. Yeah, maybe maybe PowerPoint doesn't like my presentation and just wants me to be done with it. But okay, I'll just go back and forth. Okay, yeah. So as I said, so it could be something like this. So the incident response team flags some kind of payload, but most likely these are not the data scientists refining our models. So we would like to re-execute the malware how it was done before, and then basically we need this aspect of post-mortem analysis. Could also be that we collected some data in one particular platform and we want to move it to another one. So perhaps we collected something on one resource constraint device with a particular architecture, and then we want to move it on to another one. And of course, if you're looking at behavior, sorry, I'm keeping my eyes here just to make sure that that it's showing the right thing. Yes. And of course, behavioral data, it will change if we move between different systems. Yeah, so we need to recreate the same data set with the same interaction and the same sample. So how we achieve it, we basically observe, persist, and add the ability to replay all of the parameters involved in the interaction. So this includes the samples, so the malware artifacts, the execution parameters, such as how much RAM, which CPU, architecture, and so on we are giving to the environment, and most critical also the human user input. So for example, to which directory we deployed the malware sample. How do we measure reproducibility here? So for now we have only focused on performance data sets, so the resource consumption basically, and we've measured cosine similarity of the features extracted here. Yes, and one thing to note here is that the samples themselves are not deterministic, right? So we don't exactly know what they are doing. Maybe they are talking to some command and control server, giving some instructions. So the samples themselves are, of course, not perfectly reproducible themselves. Nevertheless, we've performed 10 iterations with the following samples. So here we have a botnet sample, a ransomware, and one maliciously mining crypto. And we've also implemented a reference malware, which is as deterministic as we could implement it, accessing some files, reading and writing, performing some network requests. And the key takeaway here is that we can actually collect and replay all the human user input, leading to quite consistent data sets in the end. Looking at performance, we've used the following server to perform some experiments. So it is a very normal Ubuntu VM with 4 CPUs and 16 gigabytes of RAM. And we've considered 3 scenarios where we want to measure the resource consumption. So first, when we just deployed the overall platform without any sandboxes executing, so this is just basically the backend, the front end, and all of this stuff, but without any, let's say, containers. Then if we deploy 2 containers, so a healthy and an infected one, but not executing actively any workload, and then with one quite aggressive malware in terms of system resources, so this is a coin miner executing in the sandbox. Then we measured this for 3 different things. So for the host, which is basically executing the samples, for the backend, collecting and analyzing the data, and for the front end. We can see in the idle state, it requires very few resources. Also adding some sandboxes are almost, let's say, free in terms of resources, which we sort of expected from the container-based execution. And the main takeaway here is that with this, it really depends on what kind of load we are deploying there. So if you're using something more resource constrained, like a botnet, then we could spin up a lot of them in one single VM instead of deploying one VM per sample. Then isolation and visibility. So this refers to the security of the platform, basically. So it is important to note that it is in some way the first container-based malware extraction platform. And since it's a complex piece of software, it is very hard to, let's say, prove the security guarantees. So we just try to approximate this with a simple signature-based malware detection that we deployed, let's say, below the platform. And we've used it for all the experiments, which includes more than 100 malware samples, including botnets, cryptojackers, and so on, also spanning some very popular samples and less studied ones. And we can see that no breaches were detected by this malware detection system, and also that none of the samples seem to obfuscate their behavior in the isolated environment. Of course, here this has to be taken with a grain of salt, so most likely just none of those samples were implemented to detect a containerized execution environment. The final one is on monitorability. So basically, this is the most important aspect. At the end of the day, the whole platform is only useful if we get some meaningful data. So we want to extract as much data as possible from the dynamic execution. So we have performed actually several experiments on real-world malware to assess how useful it is. So we've considered some, let's say, normal scenarios. Oops, no, not yet. Some normal scenarios, basically. For example, one botnet running passively within the sandboxes. And also some stress scenarios, so with many sandboxes being deployed in parallel to see if the overall data extraction is basically is influenced by basically the load of the deployment. We see it is feasible to extract a wide range of features, so from resource consumptions to system calls and network. So I brought just a very basic example which could help you in finding some features. Here we can see a comparison of the data extracted in the healthy container and one with a Mirai botnet. So you can see, based on the distribution of network protocols found in the traffic, we can see there is some ARP scanning going on. So some potentially network traffic could be one data source we could use to train some kind of classifier or anomaly detection system, which is also something we have done in other experiments, but I guess this would be for another day. So in summary, we've presented a platform for reproducible data mining and dynamic malware execution, with the goal of it being secure and lightweight. Also with the goal of it enabling reproducible and automatic execution, with basically presenting rich data from different sources. But basically, the key takeaway, which I would say for this presentation, is we have enabled a kind of platform to securely extract this data. But the question remains, what is actually the relevant behavior here? So we would have to simulate this with other workloads. So quite a big effort here would be to actually come up with what means benign behavior if we're looking at behavioral data. And also checking, is this actually comparable to a real system? So if we collect some data here in this environment, would some kind of classifier actually work if we move it to the real device. And yes, it is automatically moving us to the next slide, which is great. So thanks for your attention, and I'm happy to take any questions from your end.
Are there any questions from the audience? Yes, we have a hand microphone.
Well, thanks a lot. I just wonder how many malware works in a single process on Linux and behaves normally. So is that a large fraction of the Linux malware? Because I see the point in isolating it and so forth, but the practical relevance, with privilege elevation and all those things you cannot do in a reasonably well in a container.
Yes, this is something that is super difficult to say. We have only focused on if we can extract the data and if we can do so securely. But again, what we've basically not covered is how useful is this data that we have here. This is something for which we would have to use some real, let's say, scenarios. So we would have to have some, let's say, a real example like a server running Linux, or perhaps a kind of resource-constrained device where we can actually test the usefulness of this data. So we have seen from all of these malware exchange platforms, there is a lot of samples actually targeting Linux. Of course, still, Windows is the predominant one in terms of how many samples are collected, but there are a lot of them for Linux. But I guess your question sort of falls in between, and I'm not sure.
It's more on the single process one, something that actually can live within a container, behaves normally, not spawning other processes, not changing processes. Also like attached disks, other computers in the network and so forth, just the
yes, I see the
behavior.
Yeah, I see the point. I see your point. Indeed, those are some limitations of the platform. Also something we would have to check, for example, can we make this work when adding some devices? But we did find some samples where, for example, the payloads, for example, ransomware is a very good example here, where this one has been isolated and we can easily execute it here. So assuming it is already escalated and just executing the payload to encrypt some files, we can see this behavior being very, very possible to capture here. But indeed, there are some limitations indeed.
We have time for one other question. Then I have a last one. How far are you with your research in terms of timeline? Do you have time to add more features to the platform?
Yes, that's a very good question. So we have quite some time to do it. So most of the work is basically focused on this part here. So I mentioned before that all of the components in the framework could be deployed individually. So this is basically what we are currently doing. So trying to deploy the host part, even though it is still containerized in some kind of real device, like a Raspberry Pi, for example.
Thank you very much. That's a small gift from SDS. Enjoy.
Thank you very much.
I hope you like chocolate.
I do indeed.
Big applause.
Thank you.